Continuing with part C, we're asked to draw the shear force and bending moment diagrams for the shaft. So I'm going to do that just below where we've drawn our answer for part B. And so let me draw our axes. Start with the shear force diagram. So on the y-axis here, I have our shear force. That's in newtons. Always make sure to keep track of your units. And then along the x-axis, here is our position. That'll be in millimeters. So I like to go ahead and just draw lines where I know that there are reaction forces. So there's going to be changes in my shear force bending moment diagrams along those lines. And then I will start at OY. So I know that there is a downward force of 3,036 newtons, which we just found in the last part of this problem. So we're going to start with a shear force down here of 3,036 newtons. And if you want, you can go ahead and start thinking about this in terms of making cuts along the distance of our shaft. So if I start, let me do it in black. If I start at the beginning of our shaft, I'm just going to draw a section of it here, and I make a cut. We still have to enforce equilibrium all along the length of the shaft. So I have my reaction force OY here, and I'm trying to solve for the reactions of our shear force and our bending moment. I can see that my shear force is going to be equal to OY because they are equal and opposite direction forces. And my moment, assuming that I'm making this cut just after the simple support so that this distance is approximately equal to 0, my moment is also going to start at 0, right? So if I draw my moment diagram now, and I'll do that in units of Newton meters. Our first point is going to be 0. Okay, now as we move along this plot, our shear force is going to stay the same. So if I continue making cuts along the length of this shaft, no matter where I make my cut, could be here, could be here, I still am only going to have the one shear force that's equal to OY that is acting and being reacted by the internal forces inside of this beam. So my shear force is going to stay constant all along this section. But the moment changes because we no longer have this distance equal to 0. Right now, this distance is equal to x, whatever position that we find ourselves at. So the moment is going to be steadily increasing as we move from point O over to Pulley B. And I say increasing, it's increasing in magnitude, but because the direction is facing downwards, we're actually developing a negative moment. Make this a little bit bigger down here and drag down my dotted lines. So what value do we get to? Well, let's think about if we were to make our cut in the beam just before our reaction force. Then what we would have is a moment, a moment equal to OY times that distance, so 230 millimeters. So our maximum moment is going to be equal to our negative 3036 times 0.23 to get it in Newton millimeters, so negative 698 Newton meters. So I'm going to draw that point down here and a straight line between the two. This is negative 698. Okay, so we've done our first section of the beam. Now what happens? We get to pulley B and we have a force added that's equal to 3,312 newtons. So if I were to take a cut just after that happens, my shear force would be equal to the sum of the forces at pulley B plus the forces at point O. So that's going to be 3,312 minus 3,036. So now I'm at 276 newtons. Another way to think about this is, just as I'm plotting my shear force diagram, I'm at 3,036 newtons all the way until I reach this reaction force, and then I just add my reaction force here, or my applied load here, which was the 3,312. So this distance is going to be 3,312 newtons that we need to go up in our shear force diagram. So what does that do to our bending moment diagram? Well, we're still going to have the same bending moment just before this point as we do just after. We're not changing the moment arm distance. We are adding our shear force, but it doesn't change the moment arm, and it doesn't change the moment. So we're still at this point 698 Newton meters. All right, now let's keep going. So we're going to have essentially the same thing here, where no matter how far along we take our cut, our shear force is going to stay the same in this section between pulley B and our bearing C. So we've just got this flat line between these 2 points. But now our moment does change, right? Because now we're adding a different length to our moment arm. So if I were to take a cut here, say, now I have my moment caused by OY, which is acting at a distance of 230 millimeters plus the distance from B to wherever I'm taking my cut. And I have a moment caused by the 3,312 newtons from pulley B acting at that distance between B and wherever I'm taking my cut. So what this effectively does is it causes a change in the slope of our moment diagram from a slope of 3,036 newtons to a slope of 276 newtons. So we can also think of all of this in a calculus way, where the moment is, the integral of our shear force diagram. And so this point that we are now going to at the end here is going to give us, well, the area under the shear force diagram is going to be equal to this magnitude. So the area here, this was 3,036 times the distance, 230 millimeters, and negative because it's below the x-axis. So now we just have to add this area here, which is 276 newtons times the distance from B to C, which is 0.28. So if I do that, I take my negative 698 and I add 276 times 0.28, I get negative 621. And that's still in Newton meters. Okay, so we're coming to this point here. All right, and we could also do that by taking a cut, drawing our free body diagram here with OY acting down, and then our bearing with our 3,312 newtons acting up, and then figure out at this distance of 280 what are our reaction, shear, loads, and bending moments, and you would come up with the same answer. So either way works. Now let's finish this up. We just have one more step to go. So CY is now acting as a shear force here, and we can use our same trick where we know that we are just going to go up here by a distance of CY, which is 1794 newtons, so 276 plus 1794. We're now at 2070 newtons. And look at that, how nice is it that that works out exactly to the applied load at bearing A? Well, that is very nice. It's also a requirement that those two numbers work out to be the same thing for equilibrium. So our shear force diagram is done. And now the only thing we have left is to work out our bending moment. So we can do this first. Let's just try our same calculus trick where we add this area that is now under our shear force diagram. So that's 2070 times the distance of 0.3 meters. So look at that, we got to add 621 Newton meters. That is exactly enough to get us back to 0. So a good gut check for you is to make sure that at the start and end of your beam, you should start and return to 0 if you have end conditions that don't have any applied moment. So keep that in the back of your mind. Now, if we had a fixed condition on the end here, like if this were a cantilever and it had some reaction moment, then we would start with a moment here. And similarly, on the other end, if we had an applied moment to the end of this beam, then we should end at the magnitude of whatever that applied moment is. But in this case, we have end conditions that require us to have 0 moment at start and the end, and our shear force and bending moment diagrams have gotten us there, so everything checks out and looks good.